Hi, my name is Sayo and this is my custom analog keypad project. Unlike a mechanical keyboard that relies on simple on-off switches, this system measures how far a key is pressed, allowing for more responsive and dynamic input by transforming an analog input into high-speed digital signals using real-time processing, interrupt-driven firmware, and the USB HID protocol. The hardware is built around linear Hall effect sensors that measure the magnetic field of a magnet embedded in each switch. These sensors are connected to the microcontroller's internal analog to digital converter, or ADC. Instead of scanning a matrix of rows and columns, each magnet's proximity outputs a continuous voltage that corresponds to its position. These signals are read through a multiplexer, allowing multiple analog inputs to share a single ADC channel. The microcontroller cycles through each input using an interrupt-driven system, storing the result in a buffer array. This means the system is constantly sampling each key in real time, converting physical motion into 10-bit digital values ranging from 0 to 1023. The keypad system is built around two interrupt routines that handle input and processing independently. The first is the ADC interrupt, which continuously samples each key and updates its current position, and the second is a timer interrupt running at roughly 1 kHz, which acts as the main processing engine. Inside the timer interrupt, the firmware evaluates each key's movement using both its current value and its historical data. Instead of simply checking if a key crosses a fixed threshold, the system tracks the highest and lowest points reached during motion. This allows the firmware to determine not just where a key is, but how it is moving. To ensure accurate input, I implemented a system called hysteresis, which means that a key is only considered pressed if it passes a defined actuation point and is moved downward by a minimum distance from its previous resting point. In addition to press detection, the system implements rapid trigger, which replaces the fixed reset points found in mechanical keyboards. Instead of requiring the key to fully return past a threshold, the firmware tracks the deepest point reached and allows the key to reset once it has moved upward by a configurable distance. This creates a dynamic system where both press and release points depend on physical motion, allowing for significantly faster repeated inputs. However, working with analog signals introduces challenges, as the sensors are sensitive to electrical noise. To address this, I included filtering directly inside the firmware using two parameters, press sensitivity and R-trigger sensitivity. These values define the exact downwards and upwards travel distance based on the ADC value required to register an action, preventing false presses or releases due to noise. Additionally, a lockout timer ensures that once an event is triggered, the system ignores any oscillations for a short period of time. Finally, once a valid press or release is confirmed, the firmware sends the corresponding command to the computer through the HID protocol. Beyond the switches, the keypad includes a rotary encoder that provides media control via quadrature encoding. By tracking the two square waves that are 90 degrees out of phase, the system can detect clockwise or counterclockwise rotation, which translate into volume up for clockwise and volume down for counterclockwise. Furthermore, the button has been given multiple functions, supporting a single and double click action. For a single click, it can pause or play a video, and for a double click, it will turn off and on the rapid trigger function of the analog keypad. To provide real-time feedback, the system uses an OLED display to show each key's raw ADC value, its press or release state, and a visual bar represents each key's travel. This interface acts as both a debugging tool and a calibration system, allowing me to see how each movement translates into digital signal and also allows me to fine-tune actuation points later. My name is Sayo, and thank you for listening.